Hello everyone, welcome to topic 6.2, energy diagrams. By the end of this, you should be able to represent a chemical or a physical transformation with an energy diagram. Some of this should be review. We are also going to introduce this equation. The heats of or enthalpy of reaction is equal to the sum of the enthalpy of formations of products minus the reactants. So we're introducing it here, but as you can see in this note, we will come back to it in later sections. So starting with our notes, an exothermic reaction sees energy being released from the system into the surroundings, thus heat exits. So exothermic, exiting, so it leaves the system. The products then are lower in energy than the reactants because you are releasing energy. An endothermic reaction, we see energy being absorbed by the system from the surroundings. So heat is entering or goes into the system. The products then are higher in energy than the reactants because the system is absorbing energy. These relationships can be shown in graphical form using a reaction energy profile as follows. These are reviewed from sections 5.6 and 5.10. So here we see an exothermic graph where we see this is our activation energy, and so our enthalpy of reaction is shown here. So we see that the overall energy for the system goes down. So this is an exothermic. Our delta H, or enthalpy of reaction, and it's not a standard state, so we don't need that, would actually be equal to this energy released, and because it's being released, it would have a negative sign. On the other side, where we have our endothermic reaction, we see our activation energy, but we see that the energy of the system is increasing. So reactants increase as they get to products. So we have an increase in the energy. So energy is being absorbed, so it goes up. So our delta H, or enthalpy of this reaction, would be a positive because it is absorbing, that system is absorbing energy. The difference in the energy of the products and the energy of the reactants is called the enthalpy of reaction, or heat. Sometimes it's called the heat of the reaction, and this is represented as delta H sub Rxn, Rxn representing reaction, and has generally the units of kilojoules per mole. And this is our overall expression for that, to summarize it. We'll dive in deeper to what that is, but if we know the Y values for the reactants and the products, we can determine this ourselves. We should also note that the sign for delta H is negative for exothermic reactants, since products are lower in energy than the reactants, and positive for endothermic reactions since products are higher, and we wrote that on the graph above. On the reaction pathway diagram that was above, delta H is labeled as the difference between the energies of the products and the reactants. The activation energy, or EA, is the necessary energy to start the reaction. It's used to break bonds or intermolecular forces of the reactants. The activation energy of the forward reaction is labeled as the difference between the reactants and the peak of the graph. Remember from topic 5.6 that the lower the activation energy, the faster the rate of reaction. So a little bit of review throwing in here. Looking at the exothermic two exothermic reactions where we see a small activation energy and a large enthalpy change versus large activation energy and a small enthalpy change. Okay, so these tend to be inversely related, where we see a very small E, but due to the nature of the reactions, we have a large enthalpy, and vice versa, comparing these graphs. So the activation energy, as a reminder, is used to break bonds and or intermolecular forces, while the energy that is released from the reaction comes from the formation of bonds, new bonds and or attractions. If more energy is released, than absorbed, then the reaction is exothermic. If more energy is required or absorbed in the process of the reaction, then it is endothermic overall. Catalysts, as a little refresher, are added to reactions to increase the reaction rate. They are not consumed in the reaction. Some catalysts provide an alternate pathway with a lower activation energy. This is shown on the reaction energy profile as follows, with this red line here, showing that that is the catalyzed reaction. Okay. Please note that the delta H is not changed by a catalyst. So adding the catalyst, the energies for your reactants and products is still going to be the same. So your net energy will not change. The only thing that changes is the activation energy and thus your rate of reaction. So let's review some of these concepts and apply them. So looking at this reaction, draw a reaction pathway for this reaction. Label the products, reactants, and the enthalpy of the reaction. So a reaction pathway is the graph. So we're going to set up our y and x axis. On the y is energy. On the x axis is the reaction progress. And then we look at our delta H. We see that this has a negative sign, so this is exothermic, which means that my system is going to release energy. And since it is releasing energy, that tells me my products should be low and my reactants should be high in energy. So that when I decrease and I look at the overall change in energy here, reactants to the products, this delta H is my enthalpy of this reaction, the difference between the reactants and the products, where this is my reactant and this is my product. So we have labeled our products, we have labeled our reactants, and the enthalpy of this reaction. Okay. So now we're going to draw, but with a little bit more defined labels. So our reactants energy is 40 kilojoules per mole. So we're going to start off at 40. The delta H is negative 15. So 40 minus 15 is 25. That tells me that my products have to be at 25. So that my delta H is negative 15. It goes down by 15 kilojoules per mole. My activation energy is 40, so that tells me that the overall peak has to be 50. So 40 plus 50 means that my total peak has to be at 90, because that would mean that my activation energy here is a total of 50. And then it should drop down to connect to my products. So my reactants change into my products. When we look at this, we see that the reactants, the product's energy is the 40 minus 15, which is 25 kilojoules per mole. Looking at the reverse reaction, we would need to look at what the activation energy is for that, and that would actually be the original activation energy, and then we have this additional height here, and we know that that is 15. So 15 plus 50 is 65 kilojoules per mole, because that is the total energy required to climb this hill going the reverse direction. And then finally, using a dotted line, show the curve of the same reaction with the catalyst. Now, remember from our notes that the catalyst does not change the enthalpy of reaction, so products and reactants stay at the same energy. We just add a dotted line that shows a lower activation energy. And that would be the one for our catalyst. Okay, that concludes these notes. Please try the You Do section on your own and check your answers as you go. Thank you.